Okay, recording started. Yatindra, you want to say anything, or I just?
Yeah,
Sorry.
you can go ahead, sir.
All right. Yep. Thank you very much for joining us here this Sunday morning to learn a little bit about molecular modeling with a very modern piece of software. I have 22 slides that I want to show, and
Once again, Dr. Jagan, it is requested to all of the participants, please mute their mic.
Yeah, I simply forced it. So I mean, as a moderator, you and I have the capability of muting everyone. So I just did that. So it's only Yatindra and myself. Actually, even Yatindra is. Even you are muted. Okay.
Yeah,
Well, maybe
yeah.
All right. Okay.
Go ahead.
All right.
Go ahead. Thank you.
Okay. Anyway, so I have 22 slides I want to show, and then I want to spend a lot of time working with the program. So it will be roughly about half and half. Talking, using PowerPoint and showing you things that you can do with the program. So, but before I start with PowerPoint, I want to start with a quick example, and before I get really to the first slide. For that, I will share my screen and stop PowerPoint. Share my screen and minimize PowerPoint and start Spartan. You should be seeing my desktop currently.
Yes.
And the program is loading. Okay, make it full screen, and hopefully you are there. So we are here in the Spartan screen. I will quickly build a model which I have used before in other presentations, paracetamol, just a painkiller. So which would be acetamide. So I will build here a carbonyl group and attach here a nitrogen and make it acetamide, and then attach a phenyl group and make it here phenol. Make it here an hydroxy group here. I clean this up, and then I here convert to a 3D model. I can see here immediately I inadvertently put a nitrogen there, so this here should be a carbon. And if I go back now for hydroxyphenyl acetamide, so something related to acetamol. So if I have a molecule like that, I can here go to the Spartan to a built-in database of about 300,000 molecules that we will look at more a little bit later, and replace the model. So here's the model, and I can go straight to surfaces and look at things like the electron density for this molecule, which would be like this, or the if I want to look at the highest occupied molecular orbital, which is like this, or I want to calculate the electrostatic potential map, which we'll look at a little bit more later, and which is being calculated on the fly, and should be there in just a second. Here is sort of the trademark Spartan picture that you will see in all organic chemistry textbooks around the world these days. So there's furthermore, I can go to, if I go to the spectra dialog, and I can go to look at here, calculate carbon-13 spectrum. So here I'm marking here. So you see, I'm now probably on around about 15 or so mouse clicks so far that I've spent on getting to this model. I can look here at the proton spectrum. Here with the including coupling patterns and so on. So if I want to now take this model here and generate a new related molecules, I can go to the 3D build menu and select the substituent builder. Let's say here, put here an electron donating group or here alkyl groups on this side and electron withdrawing groups on that side. And then I can here generate a list. Now I'm probably in around 20 mouse clicks. And display the spreadsheet for this. So the program has, so in about 20 mouse clicks, I've now got here a list of structures, with various substituents, so that I can further analyze, so where we could now really dive into the chemistry. So about 20 mouse clicks, we have gotten this far. So that was, I mean, basically the point I was trying to make. So I will minimize Spartan and go now to my PowerPoint slides. So, and make this full screen. And to get started, so really with the webinar, to ask the question, how did we get there to this pretty powerful piece of software that allows you with 10, 20 mouse clicks to get an awful lot of information. So it all started 54 years ago, longer before the majority of you, I imagine, actually were even born. Wave Function our company was founded by Warren Harry, who you see here, who was a young student back then in John Popel's lab at Carnegie Mellon University in Pittsburgh. And sort of his first big project was writing an SEF program and an integral program. So the problem is evaluating all these two electron contributions to the Fock matrix. And so they polished this 1968, 1969, 1970, they made it available to the public through something that the older participants of you may remember. So there was something like back then called QCPE. I think it's obsolete now. And this program was called Gaussian 70. And it took quite a while actually for the algorithm to get published, 1978. So this was really a groundbreaking paper that actually documented what was happening in this program. So in 1991, Wave Function was founded. The first release of Spartan appeared. This was, Windows had barely appeared on the scene. This was all even prior to Windows 95. So everything was Unix based. 1998, so the world recognized, the accomplishment. John Popel and Walter Kohn for density functional theory won the chemistry Nobel Prize, and the remainder basically is all history. So in 2000, as we are speaking, 2021, molecular modeling software is really present all over the world. There are Spartan copies in really exotic places. I don't want to get now into list examples, but really quite obscure locations, universities. It's used everywhere. So the two more slides on what is the essence of Spartan. So Spartan is actually a collaborative product from two companies. One company is Wave Function, so founded by Warren Harry, who is the CEO to this day. The other contributor is a company called QChem that also John Popel was associated with before he unfortunately passed away. Now basically the scientific head behind all this is Martin Head Gordon at the University of California, Berkeley. And there's a ton of contributors. We put it all together, and the whole idea is to give bench chemists, not only theoretical chemists, but chemists, who are in the lab making compounds, who are doing real wet chemistry, one product that they wish with a finite learning curve. So one product, one interface to learn, so that they can take advantage of these modern methods. So here, basically, so the four missions Wave Function is on, for 30 years now. It's hard to believe we have been around that long. Make molecular modeling easy and accessible. Get it? This was already in the abstract that I hopefully got you interested in attending this webinar. Get these methods out of the ghetto of our experts. Provide something that does require a little. There is still a learning curve. It's not like you don't. There's no free lunch, literally, but something which was intuitive, where there's an all-in-one approach, where the technical jargon is minimized. It's not eliminated, because we do need to make the connection with the acronyms that you see in abstracts, and so you will see later on some jargon, but we are trying to minimize it, at least not to overwhelm users with it. Point B, define, assess, and promote standard methods. Very, very important for really popularizing molecular modeling methods. If everyone uses something different, this is not going to help with clarifying things and with moving the field forwards. We have to push standard methods. 3, molecular visualization is sort of a pretty obvious point, and the 4th one, which I will allude to in the very last minute of the webinar. We are on a big mission to provide modeling for education for teachers and students that is scientifically sound. There are a lot of electronic tools around which are not scientifically sound, so we really believe that we are setting us apart in that way. So I will continue with a few more slides before I go back to the program. Part 1 of the webinar really is, where can Spartan be useful? I want to spend a few minutes on the next slide, even though there are lots of words on it, and I didn't get around here to make it a nice animation where I sort of highlight them one after the other. It's a refinement I should do. So here it's just but I still want to talk about what's actually on this slide. So Spartan is a molecular modeling program where you'll be fine with hundreds of atoms, thousands of atoms. So brute force nanochemistry won't work. I mean, it's sort of, the program will show you the model, but you cannot do a lot of inquiry. Doesn't mean you can't do nanochemistry. You just have to formulate the problem in such that with dedicated reduces to a model which is with a molecular weight of 500 or less on a modern laptop. So of course, the bigger the better the machine, the more you can afford to run. But this is sort of a rule of thumb. Stick below that. Equilibrium structure, excited states, we will look at that in the program. Molecular mechanics, Miller-Placid. So this is obviously modern quantum chemistry. All this can be done. What Spartan won't do is true solid-state chemistry where you work with unit cells. If you can formulate a solid-state chemistry problem in terms of a cluster where you worry about where you saturate the surface properly and so on, you can do solid state problems, but you won't be able to do it in the brute force way where you have a replicated unit cell. So this is really the domain of physics-oriented programs where you use plane waves. There are plane waves codes around, band structure calculations. Spartan is really a quantum chemistry program oriented towards small molecules. Molecular dynamics is wave function has a molecular dynamics program, but is not sort of on the periphery of Spartan. It's not addressed in Spartan. It will do, though, very extensively. I hope to be able to show you examples of that. Molecular mechanics, which is here, and then based using conformational search, which you can wrap up with a quantum chemistry method, but with molecular mechanics, a classical method is really the way to go to first get brute force lists or get lists of lots of conformations. This Spartan is very strong in that. Transition states, reaction mechanisms, big big strength of the program. Thermodynamics, activation energies, solvent models. Explicit solvent models are very, very expensive. So we do not try to go there and sort of we do and rather offer a whole bunch of continuum solvent models. We defaults are the ones which work best. If you want, with keywords, you can overwrite this and do more exotic ones. Spectra, NMR, IR, Raman, UV vis, big. Spartan is very strong in that, and the development of calculated NMR spectra has taken a huge effort just in the last few years. Very complicated protocols that you can initiate by just one mouse click. So no more difficult than recording an experimental spectrum. Spectra, though, that are not there are here on the right side, ESR and NOR. So in fluorescence spectroscopy, we don't do that. Mixed quantum classical, I skipped that line here. You can do complicated protocols where you start with a classical simulation and then continue with a quantum calculation, but we don't do mixed quantum classical in the same model. So we just don't get into that. Orbitals, of course, molecular orbitals, that's sort of the absolute natural for the program. We don't do hybrid orbitals and natural bond orbitals because it's a can of worms. They are all kinds of definitions around. It's like we just decided not to go there. It's not impossible to do, but we don't want to go there. We just stick to conventional molecular orbitals. Here at the end, I will show that in about an hour. So QSAR-related topics like generations of libraries that you will investigate under the QSAR from the QSAR's perspective, or similarity analysis, looking comparing with pharmacophores and so on. This is in the program. However, what's not there is now sort of if you get to the into the biochemistry field, docking of proteins, we don't do that. There are specialized good programs for that. Informatics, sequence analysis-based things that you get fast or blast or something like that. We don't do that. Also, electrochemistry, you can calculate some quantities which are relevant for electrochemistry, but literally you don't do simulated electrochemical cells or something like that. So here on the right side, here is full disclosure right away. So if this is really what the only, the one thing you are working on is here on the right side of the screen, and you'll be disappointed at the end of the hour. You won't have gotten, any pointers of useful things to use in the program. We don't do this. Okay, but it's the world's the easiest to use program for everything that you see on the left side. Okay, computational techniques, and a few more minutes, and then let's start with the program. So computational techniques, here's a summarized in one slide. So first of all, you need to have a model. So typically you would, unless you get the model from somewhere else, you would create the model. You have the option of 2D sketching. You can use ChemDraw if you have the license. It's in Windows. It seamlessly interfaces with it, but you have to have ChemDraw. So we don't supply ChemDraw, but then it's completely seamless. But our 2D Sketcher, which is the one I just used when I started, is basically the equivalent of ChemDraw. But many people, they are used to ChemDraw, so sure, use ChemDraw. It's a button in the build panel in Spartan. 3D building, which is, I will show that we have, this is sort of the traditional, this is sort of the equivalent of plastic model kit. We have powerful builders there for inorganic and organic and inorganic molecules, also for polypeptides and polynucleotides. It stops short of proteins and, and long nucleic acids. So polypeptides, polynucleotides. Keep in mind, it's like you'll if you want you won't be able to do quantum chemistry or large-scale conformational samplings, on something that has 1,000 amino acids in it. It's just not possible. Spartan is very strong in terms of handling of lists. You actually saw a little glimpse of that when I took my paracetamol-related molecule and added to it electron withdrawing group, I think, and an alkyl group, and then it just hit one button and generated a library already. From then on, you can do everything, in parallel with all the members of the list, as opposed to look at one model at a time, which is sort of other programs will typically will focus on that. Spartan gives you the tools, whether you take advantage of them or not, to handle lists with relative ease. By you always select a global button, a check mark for global, and then we'll just do the list instead of one molecule. Okay, here on the left side, quantum chemistry. So this is the engine which comes from QChem, millions of lines of code to do the the most up-to-date calculations, fastest calculations, parallelized, and so on, for nowadays on a laptop that used to take months on a supercomputer. Molecular mechanics on the right side, so that's classical force fields. What else feeds into it? And conformational search, closely related to molecular mechanics, for fancy algorithms to look at the flexibility of molecules. 3 databases you can tap into. One is the Spartan database, which is about 300,000 molecules, which we will look at a little bit, which you have to once install, and then you can seamlessly tap into it. Wave function, IR frequencies for one particular model, all kinds of calculated properties, all pre-recorded. So at least as a reference, very useful, even though your particular molecule, if it's new, won't be in there. But it's a very useful reference. The chemistry crystallographic database, we also seamlessly interface with that. Again, that is a separate license, just like ChemDraw. Very useful these days for people who are into QSAR related studies, because you have over 1 million structures, not so much from the point of view of the crystallography, but simply, what are low energy conformers of organic and organometallic molecules. PDB can also be, it's a freely available database that you can simply type in the PDB identifier and you will access that. So then once you have this, now going down in energy gives you the equilibrium structure, going up in energy gives you a transition state. Database searching, obviously you'll see some few tools for that. Similarity analysis by comparing various structures, so QSAR related, and calculation of spectra. Okay, probably I should stop here and first go now to the program, so that I don't have spend too much time here on it doesn't become one gigantic slideshow. So I'll minimize this, end the show, minimize this, and bring Spartan back, and save changes, close this. And if I should make sure, am I still sharing? No, I'm not.
No, we have not.
Yes, I have to. Yes. I shouldn't. I shouldn't have stopped the share. I should have stopped the. Yes. So.
Yeah. Now we can see the software.
Yeah. Okay. All right. So we are back to. Okay, let's look a little bit at the build 2 models, calculate the equilibrium structure and look at some graphical models. So I will the 2D sketcher, the equivalent of ChemDraw, if I want to build aniline. So it's just works like this. So then here I can there's always a cleanup here, structure cleanup, and then I go back here by clicking on the glasses to get to the 3D model. So I could also I can do also build in 3D by going here. Here you see, by the way, the ChemDraw button. I don't have ChemDraw, so but here this would lead you to ChemDraw. So I can here do. Let's put here a fluorine on it. So a fluoroaniline. And so here's my model. So I will always minimize it first, the structure, minimize classically, even though here you will hardly see a difference. Now I want to compare aniline with a fluoroaniline in this case with nitrobenzene related to electrophilic aromatic substitutions. So how can I will immediately create two models. So I go to File, Build New Molecule, or Sketch New Molecule. Well, I use the 3D builder in this case. So I do a ring and hang off here a nitro group, nitro. So, and why not put also fluorine here, metafluoronitrobenzene. So now I have here in the spreadsheet, I have two models. I can show them at once. I go to here to uncouple them. So here is my aniline molecule, or fluoroaniline. Here's my fluoronitrobenzene. And I will both of them are in the Spartan database. I will I could immediately retrieve it from the database. But to show you the dialog, I will here actually go to the calculation dialog and select energy density functional. This is the default density functional model that's known in the program. Which is so there's no jargon. This is it's a mouthful. Omega B97XD. I'll have it on a slide in a few minutes. This is what we recommend. It's the sort of the safest choice these days. Not too super expensive, but better than B3 lip. Sort of it's something if you're not a theoretical chemist, you can go wrong with it. So, and there's here the global check mark, means it will do the same calculation on all the models here in the list. So I do a submit. Now I create the model Spartan, and it started. And since this was already a minimized structure, it shouldn't take a whole lot. I can look at the monitor here. Well, actually, it will run it in two threads. My computer has two cores, so it will run, one on each core. So there, you see here you can follow how the SDF calculation is running, and hopefully that should finish in I put on there the extra fluorine, which maybe I shouldn't have done, but it should finish in any moment, I hope. And I will, in the meantime, I will already request surfaces, namely I will add again the density, and I will add electricity potential map, and I will add the local ionization potential map. Is that what I wanted for? Local ionization potential map. Let me see, what's that? Yeah, local ionization potential map. So, unfortunately, this still hasn't finished. So, I can squelch it and get it from the database. So that's going to be let me do it at least for one of them. So I'll terminate this one too. So I killed this. Now I will do this here by replace it from the database. So replace both molecules will now being replaced from the database. And I can go to the surfaces dialog and show the density for both of them. Add the electrostatic potential, the electrostatic potential map, which will superimpose on the density isosurface as a color value the electrostatic potential. So this here is and I can change the style here to transparent. I will add another one, the local ionization potential map. And here where see a distinct difference, and I can change change the color value. So where you will see here meta versus ortho and para, a directing effect of the amino group versus the nitro group. So which is the by playing around, I can change the color scale here, but it was less pronounced here. If I make it even, I can't see anything. So this is all manipulable. I can also change, the size of the. This now includes 99% of the electron density. I can reduce this to 95%, reduce it to 80%, and so on. So I get an immediate visual illustration of so in effect, which of these molecules is more susceptible to electrophilic substitutions. I'll minimize that and go back to the PowerPoint, and here now show you the. Actually, I feel like I will I should have just kept it running and gone back to the PowerPoint slide, because it was about to, it should have taken maybe 90 seconds or something like that. I wasn't patient enough. But here, the relative computational cost. What I used here is density functional theory, which is this, this mouthful of a functional omega B97 XD with this basis set, so which is more expensive than B3-lib, that at least some of you, I'm sure, have used it in calculations by a factor of 2 to 5, but it is better. And so B3-lib is a cheap fallback. Here's and this here is now sort of
Dr. Jagat, there is one quick question from Dr. Zitu Payal.
Yes.
What are local ionization potential maps, and how they are different from ESP maps? Thank you.
So the localization potential will simply show you, so the color value will show you what is by adding up, the ionization energy for the energy levels, where is it easiest to pull off an electron. As opposed to the electrostatic potential map, the color value represents what is the energy of interaction with a positive test charge at that particular point. If you see a red color, it's the positive test charge is strongly attracted. So this is electron rich. Blue color, the positive test charge is repelled, electron poor. So the localization potential map is a different quantity, namely the calculated locally by adding up over the energy levels, where is it easiest to pull off an electron. So which is relevant for the for electrophilic attack of a molecule. Okay, so I hope that is works as an explanation. So now here, this slide, I wanted to make the point here about sort of the philosophy of Spartan. We do not avoid. You will see in the calculation manual these ugly acronyms. If you're really a hardcore organic synthetic chemist, these are these are really ugly acronyms, but we do not avoid them, but we choose defaults which will work for you. So all you need to know is the default is this, and if you want it quicker, go back to B3-lib. For energetics, you should use something fancier. Now, if I go back to the program and look at the calculation dialog, display setup calculations, I can do all this with just a couple of mouse clicks. I can request equilibrium geometry with a fancy model. For example, this here would be a fancy basis set. So here, this ugly this ugly method, but I request the energy using this very large basis set. But I can start from the geometry. I can go the equilibrium geometry with something cheaper. So this will be, it's all, once I click here on submit, it's just, it's off and it comes back magically. So but actually what's running is a pretty complicated protocol. Namely, it will take, and here if you want it even cheaper, I switch here to B3-lib. It will calculate with B3-lib and this basis set, the equilibrium geometry. So we'll do, minimize the, change the geometry until you find the energetic minimum, and then calculate once you're at the bottom of the well. Now calculate, with a fancy method, fancy functional, fancy basis set, the energy. So, which is sort of the best you can do. If you always want to do, the use the most complicated methods, sort of brute force, you're going to draw in computation time. So we are providing tools so that all these things become doable in finite time, so that your jobs will finish in minutes or hours at most, but not weeks and months or the way it used to be. So that's the philosophy of the program. What I meant on an earlier slide, minimize the jargon and make it easy for the user to use. There's a bit of a learning curve, so but it's as easy as you can possibly as you will get it, compared to other software that you can get for. There are quite a few quantum chemistry programs around, and I will leave it at that and go back to my once again to the slides, because I keep sharing, so then I'm here. So quantum recombinant functionals. So now let's look a little bit at applications. We already started with that. So that's really the main part of the webinar. So structure and energetics, transition state searching, and conformational search. So structure and energetics, you'll just saw an example for that already. So let's do something a little bit more ambitious, namely finding transition states. And then I do conformations a little bit later. So I'll here on the topic of finding transition states, and show and go back here, and I will create a new before I create the new model, I simply show you here in the calculation dialog the various options you have. So this sort of maps onto what I had on my slide. Energy, so that's a single point, given geometry as the user defines it. Equilibrium geometry, go energetically downhill. Transition state geometry, that goes energetically uphill. The problem with that is going uphill is not as straightforward as going downhill. The chances of going astray are considerable. And I'll show you some tools we provide in order to facilitate that, in order to a helping hand, in order to find transition states more reliably. Then conformers we'll look at a little while. Energy profile has also to do with reactions. NMR spectrum comes later, and this year's QSAR related at the end. So here now, transition state geometry. Before I go there, I will show you the type of handholding we provide. For that, I will look at a simple chemical reaction, cancel, and create a new model for classical Diels-Alder reaction. So I will use this. You can do it also with a 2D sketcher.
There is one question,
Yes.
Dr. Jurgen,
Please.
from Noor Muhammad Nasir.
Okay.
Can Spartan calculate global potential energy surface per molecule where repeating unit n is equal to 1 to 20?
And what was the last?
Where repeating unit n is equal to 1 to 20 range. I believe
1 to 20 range. I'm not sure what he means by 1 to 20 range. Calculating the global minimum is, if I go here to setup calculation. So equilibrium geometry means that the program will use a sophisticated algorithm to find, and not trying not to get trapped in shallow neighboring minima. It makes an effort to find the global minimum. Now, finding the true global minimum is an unsolved problem in science. I mean, it's like some, you can check in Wikipedia, sort of in the math section. It's like or it's in the NP complete problem. You can never be sure that you have find the true global minimum. It's all we can say. This is a very good minimizer, which has decades of experience behind it, to find make a good faith effort to find the global minimum. In chemistry, though, I think people usually very, very often overestimate the significance of the global minimum. Because you think about it, most molecules, especially in organic chemistry, are flexible. They are torsion angles. They are rigid molecules are really the exception. They are not the rule. So things are flexible. Things being flexible means you're dealing with conformers. So, and it's like an issue which is completely underestimated, I believe, by many, practitioners of the art. So that you really molecular modeling program like Spartan allows you to actually explicitly look at this, namely calculate conformal distributions, look at what are forget about the lowest one. Equilibrium conformal would be the lowest one, but what is actually the distribution are the other ones which contribute, because once you have flexibility, you always deal with multiple structures at once. You have to Boltzmann average it and so on. We have actually provide tools for that. So I'm a little bit here. This is a little bit of pleading with look at conformers more rather than completely being focused on ground state structure. So because flexibility is a big issue in chemistry. Okay. There was the question of energy units and so on. This all can be, of course, can be changed, and this is natural for the program. Okay, I was here about to build here. Built here butadiene, and I will plug on the few cyano groups, so to make it more interesting. And I will do a classical Diels-Alder, so where I do where I set it up like this. Now I have a tool here. I can which is in the where's the build menu guest transition state, which is there should be an icon for there's the icon. Yeah. There's the icon for guest transition states. I mean, these icons are all replicated in the menus. So it's guest transition state. So now here is I can do sort of the equivalent of oops, I'll undo that and go from here to here and from here to here. So here I do arrow pushing just as we do, in organic chemistry class. And then I'll click here on the right, on the lower left, and the program will search a database of about 1,200 pre-calculated transition states and try to find a match in there. It will, and if it doesn't find an exact match, it will try to interpolate between whatever it finds there. So now here I have, this was calculated before, so I have a reasonable guess. And now if I go into the calculation dialog and select your transition state geometry, and let's say, this B3lib, I still also like B3lib because it's cheaper than the default, but and we're to click here on submit, my chances of going energetically, let me do something really cheap, semi-empirical. Let's see whether it finishes while we are watching it. And I'll do submit go up.
In the meantime, one question is there, Dr. Jagan.
Yes.
How we can calculate transition state organic reaction to product if reaction path go through radical cation or radical anion or only radical in photochemical reaction?
Yeah. So when you define in the calculation dialog, so the charge and whether you have radicals, think about it, it's in quantum chemistry, all you really supply is where are the nuclei and what is the total number of electrons. There's nothing else really. So there's some here too. So I select the charge here and I select, how many ampere, do I have a doublet, singlet, doublet, triplet or so, number of ampere electrons. And then the the algorithm, the Hartree-Fock theory, density functional theory, whatever, takes care of everything else. I don't have to specify, where is this, the fact where this, if it's a radical, where's the unpaired spin? It's an output of the calculation. I don't have to provide this input. I have to, I declare where are my nuclei, and then here charge and unpaired electrons. That's it, and then it takes it from there. If there are unpaired electrons, so now it will use it's more sophisticated algorithm than if they are not unpaired electrons. So-called, replace restricted Hartree-Fock theory, for example, by unrestricted Hartree-Fock theory, and so on. But this is all behind the curtain, so you don't have to worry about that. The program will do that, will do that for you. You just have to, it just has to be consistent. Charge and number of unpaired electrons have to be consistent. You cannot have something that doesn't where you cannot draw a correct Lewis structure for. I mean, then it will complain because it's impossible. But otherwise, but everything else is an output. Okay, so I just went here and this finished. It did semi-empirical. So if I calculate a transition state, I always should. I had selected that in the calculation dialog, the IR spectrum, because what I want to see now is I will go to the spectrum dialog and I will go to IR calculated, and here's for the transition state of this reaction. So here I can, in this case, I mean, this is not a molecule you can bottle up and put in a flask. It's a transition state, but you could see the same would work for, the program shows you the vibrations of the that associated here with the various normal modes. So what I want to know is there one imaginary frequency because it's a saddle point. The transition state is a saddle point. To go over a saddle point means that in one direction, in just one coordinate of the n-dimensional space, just in one dimension, you're going over the hill. You are not at the bottom of the well. And this is associated with this, so it's the opposite curvature associated with an imaginary frequency, which we see here. So that is the crux really of finding transition states. If you don't start with a good guess, and if things go astray, which can happen very easily, anyone who has calculated things like that has experience with that. It's very easily happens that you will get multiple imaginary frequencies, which means it's not a true saddle point, and so on. So here, no, everything is clean. So this here is the frequency here for the transition state of the reaction. I can actually put this in a list. I haven't make a list amplitude. So this here went into a I just took, 11 steps of this vibration were put into a list with one mouse click, and here I can scan through this, and I could calculate now. If I would want to calculate now the let's say the electron density just for this around this transition state, I should have used a bigger. Let me close that. No, and go back here and make a longer list. Make the list longer, make it 20 members, and make the amplitude a little bit bigger. Make it 1 angstrom. Run, enter, make list. So, and now I can go like this. And now I want to calculate the electron density for each step along the way around the transition state. So I will go to setup, calculations. So now this is a list, and I will do a global calculation for all the members in the list. And I will calculate the energy. And again, just semi-empirical. So because it's bad quantum chemistry, it's sort of a bit obsolete, but it will finish in no time. And I do, and I immediately will request also the density surfaces at density. Global is set, and then submit the whole thing. And this should take, even though the program will solve the Schrödinger equation 20 times for each step along the sort of the reaction coordinate they are going over the hill, using semi-empirical quantum chemistry, which is no longer, really only good these days for getting a guess. But so here we are, and I'll put this here on transparent, and let me do density with a higher density value. Okay, this here is closer to the. So you see here for this reaction, and I can always, if I select the surface in the lower right corner, I can change or make it, if I make it the mesh style here, people like that. So I can get an illustration here of a chemical reaction. So what is the total number of mouse clicks that got me here? I didn't track it. I guess you could take the video recording afterwards and count it, and maybe 30 or something like that. So it did not, obviously, I'm trained in using this program. which is different from never having it used before, but it's a finite learning curve. And if you go through the learning curve, you can create incredibly powerful animations. And I will point you immediately to the before I continue with further examples, to the manual of the program, which is a PDF file. If I go to first I go to the Spartan 20 manual, and there are two sections in the manual, and since I'm sharing my screen, you should see it all. So page display, two-page scrolling. So this is it's a 681-page document, but you do not have to read the 681 pages. Don't worry. So it will have three-quarters of it is sort of a conventional manual, going through all the menus and all the options and so on. But there's the beginning of the manual. There are tutorials which are exceedingly well written, where you spend some quality time with it, building organic molecules in 3D, sketching organic molecules in 2D. You saw me do examples of that already. Spectra and properties from the database. Groups of organic molecules, you already saw that. Inorganic, organic, metallics, chemical reactions. I showed you sort of a similar example. Medicinal chemistry, I'll show you one actually towards the end. And flexible molecules comes next. So they are about, these tutorials are very well written, and if they require a little bit of quality time, but you'll feel incredibly empowered after working through them, and you will be amazed what you can do if you just willing to make this relatively small investment. So which is different from the investment you have to make for lots of other quantum chemistry programs, where basically you turn it over to an expert who knows how to use it. These tutorials are also in the program here in the options menu, in the activities menu. They're here also separate as tutorials. You go here. These are simply the chapters from the manual. Walking through Spartan, groups of organic molecules, chemical reactions, and so on. So that's the learning curve. But you'll be incredibly empowered if you work through those. There's a second thing here in the.
There is one question, Dr. Jurgen, and from Dr. Ria. How we can calculate thermodynamics terms, likely enthalpy, entropy, free energy, and so on.
Okay, that's good.
For reaction having multi-step mechanism.
Multi-step mechanism. So you would do this now by creating a list, for the multiple steps. So then you will. You can also do everything sort of one by one, but if you want, to streamline it, you create a list for the individual steps or for all the molecules that contribute to the reaction. And then you use the global option, to do all the calculations. Now, how to calculate the thermodynamics, I'll show you, and then confirmations. So I need to keep track here. Quickly here, after I've shown you topics, here is topics, which is also, these are also in the back of the manual, so which are well-written chapters, calculating NMR spectra, calculating infrared spectra, and so on. Thermodynamics, there was just the total energies in thermodynamics, kinetic energies. This was just the question that came up, and I'll show you simply an example, but you will see here, if you want to find out about it on your own, two-page scrolling. So here's at first a little bit of theory behind it. What transition, definitions of activation energies and so on. One atomic unit is 25 kilocalories per mole and so on. Pictures here, transition states. Sort of this is basic physical chemistry. It's not the most advanced statistical mechanics. It's basic physical chemistry. Boltzmann weighting here, and So, and hints how to apply the program to this particular topic. So now I will do for a molecule, and I will actually use the same molecule that I will then do conformational search for. So I will build something again. So I will build.
We are getting some questions. We will address all in last, I feel.
Yeah. So
Yeah.
I will
Thank you.
do. Oops! I don't want to have too many chlorines in here. Okay, and so this here is like something, actually a molecule which is not in the database. So even the 300,000 molecules doesn't include this one. So it happens to be it's a new molecule from the point of view of Spartan. So if I go to the setup dialog, and I will do here just an energy and quickly Hatry Fock, something cheap just for the calculate. And so this will, actually, I should have at least minimized it. That was not good. I should have at least minimized it classically. So let me, because I make up examples on the fly sometimes. So I will kill this. Look at this here. I mean, I built the molecule with a builder, and I violated my own rule, always minimize the energy first classically with a force field, so that those two hydrogens up here, won't overlap. So now it's maybe not at least sort of a classically minimized structure for this aromatic hydrocarbon. And now I will do again my calculation and Hartree-Fock 631G. And actually, let me request QSAR properties too, and submit this, and it should come back in quickly. Single point. So, and then we'll look at the properties dialog, which is here, which is right now still faded out, but so there are 98 electrons already in this system. So second time today that it doesn't finish as quickly as I was hoping for. 35 seconds now when you're waiting for it is a long time. So 46.
In the meantime, can
Yeah, crack, yeah, it's just finishing here. So 52 seconds, yes. So it's like some, I did not, carefully curate the which models I would use. So it wrapped up. So completed. So I go to the display properties dialog. So and I go here to thermodynamics. So here's 0 point energy pending and entropy pending, free energy pending. So what I need for that is basically the vibrational structure of the molecule. So I will have to go back to calculations, which I forgot to do, and select here IR. So and I'll do IR and semi-empirical submit. And now these numbers here will become populated because it uses statistical mechanics to calculate 0 point energy and entropy, free energy, whatever. You select the unit. You can choose the temperature that this is for. For the free energy. You can select the scale. I mean, there's lots of things that are adjustable. So that's sort of natural for the program, and I can if I do this now, you ask for a reaction mechanism. So a spreadsheet, I would here would have not one molecule but other molecules that are other species that are relevant, and I can add simply here, the energy in kilojoules per mole for if it's minus 42 kilojoules per mole for this one. Now, if this was a list, now you would get the equivalent numbers here. Then there are tools actually even to there's a reaction dialog where you can feed in, you define products and then reactants, and it will calculate. You have to balance the equation. It will calculate even reaction energy and things like that. So that's all natural for the program. If you want to use really the fancier tools that are available, then once in a while you may have to look at the manual. So okay, so this is thermodynamics. No, conformers. I made a sort of a defended or argued that conformer, the issue of molecular flexibility is often underappreciated in chemistry. So I will go to here now. Go to the conformer distribution for this molecule. So they are using molecular mechanics. With conformers, I always want to start with molecular mechanics. I mean, I can do density functional, but the risk of immediately falling into a black hole is great, because I mean, these are a DFT for every possible conformer. That can get very expensive very quickly. So you start with molecular mechanics. We keep all the ones which are 40 kilojoules per mole above the lowest one, and then we submit. And so that my usual worry. Now I hope this will finish in. Yes, it did. So here it immediately created new. This here was the model I worked with. It immediately created a new tab here at the bottom, so which contains now the conformers. Here it goes through too fast. So where low energy conformers, and I can look at the display spreadsheet. No, the energy. So it found six reasonable conformers within 40 kilojoules per mole of the lowest one. And if I do the energy here, so it found this one was the lowest one using molecular mechanics. This one was the least favorable one of the six. So 32 kilojoules per mole above this one. Why are these numbers positive, not negative? Does it mean it's unstable? No, these are molecular mechanics, classical force field energies. This is not quantum chemistry. These are classical force field energies, which are parameterized to minimize the strain energy of a molecule. The zero of energy is completely arbitrary. This is not, you have to do, this is not a first principles calculation. It's completely arbitrary. All we can say is this one is, if I do here, show these two, and then uncouple them, what we can say is that the conformer on the left is 32 kilojoules per mole lower in energy than the conformer on the right. Okay, so that's the relevant information. There's no significance to plus 107, plus 139. That's different once you start with quantum chemistry. I mean, I could now take these six and do a DFT calculation for these six. That's certainly doable. I mean, that's not no big deal. So then I would get here, absolute energies which are the negative, and which are where the absolute value actually is informative. So that's the issue of confirmation. Let me go back to my slides, minimize Spartan, go back to the slides, and then transition to make this full screen. So what else did I have here? Graphical models, because we are already now an hour and 50 minutes into the webinar. I will just leave up the slides. So you saw bits and pieces of this. Electron density isosurfaces completely You saw examples. Molecular orbitals, it's pretty obvious. Electrostatic potential maps, you saw examples. The electrostatic potential is something that people sometimes have a little bit difficult time to wrap their head around. It's the interaction energy with a positive test charge anywhere around the molecule. So it measures where is it electron poor, where is it electron rich. Localization potential, I said a little bit about that. Spin density, this kicks in once you have radicals. Where they are, unpaired electrons. They're always, the maps are often more useful than the isosurfaces themselves. The maps arise by mapping each of these properties, localization potential, electrostatic potential, or molecular orbitals even, map them onto the electron density isosurfaces. That's the significance of the maps. Slices look very, very, very impressive. I don't have time now to show it, so I should have actually. Would be nice if I had a pre-calculated example. I don't. So slices can be calculated, which look beautiful. So for graphical models for electrolytic and nucleophilic attacks, it's all documented in the manual. What works. Spectra, because I want to do spectra and then a little QSAR and then wrap it up. So spectra calculation is the NMR, UV, and infrared are available, not ESR. So UV vis, Raman goes along with IR. So that's basically it's just complementary. The calculation of the spectrum, you saw it very quickly. Though should show one more example. I'll do the and show minimize, go back to the program. And let me see, do I have a model which is fluoroaniline? Okay, so I will hide the other one. And turn off the surfaces. So this was in the Spartan database. So I will do replace EDF2. And so the NMR spectrum is basically pre-recorded. So so what is available is both always proton and carbon-13. Carbon-13 nowadays by far the most important one. Proton spectra, of course, also. That's how it all started. You can pull up if I keep calculating proton spectrum, I can pull up the experimental spectrum if it's available here without coupling constants. Let's see, downloading. Yeah, it goes to a database at the University of Cologne for 50,000 molecules. So 3-fluoroaniline is obviously not in the database, so it didn't find it. If it's one of the 50,000, you will pull up here the experimental spectrum. 2D NMR is represented, the most important methods, COSY, HSQC, and HMBC. The nuclei other than carbon and proton NMR are also the chemical shifts are calculated, but you have to look them up in the output. I don't think the spectrum can be shown in a straightforward way. So actually, the program has so much stuff in it, I'm not even 100% sure of that. But I think definitely the list of chemical shifts is there for fluorine, phosphorus, and so on. Now, the chemical shifts for NMR are calculated but from scratch, but they have empirical corrections on them. So we have spent a lot of effort, to really push the methodology forward and to get spectra which can be used actually to correct, to help with the successful interpretation of experimental spectra. And coupling constants by default come from the Karplus equation. They can also be calculated completely from scratch, but it's very costly. Now here, for flexible molecules, Boltzmann averaging of conformations, I want to quickly draw your attention to that. This is something, a very, very complicated method, which is all sort of behind the curtain, one mouse click you can initiate. They go to NMR spectrum, and I show the details. So I can, for a molecule, I can request a Boltzmann averaged NMR spectrum. So it will do first conformational search, find relevant low energy ones, then switch to a sequence of increasingly sophisticated density functional methods in order to get the energetic weights correctly, and then average it all at the end. And what gets spit out is a Boltzmann averaged NMR spectrum. It's a complicated protocol that we have worked out and which we have applied to lots of natural products, and we have found that the incorrect assignments are a dime a dozen in the literature. There are a sequence of papers on that from wave function with collaborators in universities. It's the methodology or first principle calculations have advanced to the point where they can really help to fix, misinterpretations of experimental spectra. So that's on the NMR issue. On the UV and IR, I will just mention it quickly on the corresponding slide. So full screen. So UV widths limited. You need to use either Hartree-Fock or the density functional theory. Can do it with something simpler. Little bit time consuming. By using the so-called Tamm-Dankoff approximation for DFT, you can speed it up. It's less accurate, but it will be faster. Again, comparison with experiment is possible with one mouse click with a NIST database using 1,500 online spectra. You can input your own spectrum if it's in the JCAM format. IR Raman, frequencies calculated from scratch, but with scaling factors. It's a long story behind it. It's first principles, but you have to tweak it in order to make it all work. So, and that's what we do. And the accuracy is good, very good these days. So line shapes obtained from fitting to Lorentzians. Comparison with experiment, 7,000 online spectra in the NIST database. Again, your own if you use the JCAM format. So my last topic for the last few minutes is something here related to QSAR and similarity analysis. And I want to show an example literally from the tutorials in the manual. So if you get a trial license of the program, you can try it out yourself. And which is by first starting by minimizing this, and by accessing some of the databases that you have access to. So I will go back to Spartan and build a new molecule, and I will build, in this case, trichlorophenol. I'll do it here with a 1, 2, 3. So, and I will now so I have my molecule here, and I will search in the 300,000 molecule first Spartan database, which is about a 20 gigabyte file. So, which you need that much disk space, but everyone now has 20 gigabytes these days. So, structure query, I will use for all structures which can be this motif here, where anything can hang off here on the left or on the right. And then I will go to the databases, and we'll start out with the Spartan molecular database. Let's see, search SSPD by structure. Yeah, let me do all this, and EDF2 will be fine. I will run this and start the search. And so it goes through the 300,000 structures. So it found 9 hits. And for example, here is one. So now I can retrieve this into a new document. So, oops, I didn't retrieve. I think I didn't hit the retrieve button. So databases. So I select this one and then do the retrieve. There it is. So here's now one that's, this is sort of a trivial example. One of the 9 hits that found among the 300,000. I could play the same game with the Cambridge crystallographic database. So, oops, I have to go back to the previous one here, and so where my structure query was like that, and I will go to databases. Go to CSD. So this is Cambridge if you have it installed. So that's, a separate license. I think it's also pretty common in India. So, it's present in most academic institutions around the world, for many at least. So here we'll do search in the organics section of the Cambridge crystallographic database. Click on OK and do the search. And so here it found 25 hits. So, like for example, you typically, in what crystallizes always are adducts of multiple things. So if I do now retrieve, I can though get rid of the other stuff, extraneous fragments. So I will do a retrieve of what's in the data in CCSD, but will delete extraneous fragments, repair bonds, grow hydrogens, because data both in PDB as well as the Cambridge database, are typically quite dirty. So I do an OK and do a retrieve. And here's now my cleaned up structure as it came from the Cambridge crystallographic database, and very valuable source because you have over 1 million structures of low energy conformers of organic and organometallic molecules. Okay, so I will now do the show an example of generating a similarity library and similarity analysis. Was that a question? Oh, now I get an echo.
You can type also in the chat window.
So, mute microphone. I will. Okay, I muted everyone. Okay, and Yatindra, you are still unmuted. Yeah, so you are on request to turn on audio. So yeah.
Please go ahead. I can unmute myself. Please go ahead.
Okay. All right. Okay. So yeah, there was feedback because someone had the microphone open. So okay. So I want to generate a compound library, and by going to generate a similarity library and do a similarity analysis. So I'll go to Spartan, and my prop is going to be the morphine molecule, which is the subject of a tutorial in the Spartan manual. There's again something open somewhere.
Please go ahead. I have unmuted. Go.
Okay. All right. So here's the morphine molecule. So the question is, we want to look at at the SSPD, at the Spartan database, molecules which are, have similar to this one, given the fact that the structural motif that actually make morphine the compound that it is, this very powerful and very dangerous compound. So it has here a phenol motif here, and basically a tertiary nitrogen motif here. So I will create a model which for a phenol and a model of trimethylamine representing sort of the absolute minimum of the phenol motif and the minimum of a tertiary carbon, and now request a structure query where I will 1, 2, 3, 4, 5, where anything can hang off anywhere on this phenol ring. Anything, not this one. One, and anything can hang off this methyl group, and anything can hang off here at least for one of the free valences here of the third methyl group. And now I will go to search databases, and I'll go to SSPD, and we'll do my search. So you can recreate all this if you have with a trial license of the program, just following the tutorial in the manual. So here's I will just pick the one at the top because it's the easiest one, where generating the similarity library will be the quickest. So it's this molecule cephalene. I will retrieve this. So now I retrieved from the Spartan database a molecule, cephalene, and now the question is there's a lot of flexibility in here. So is it is this molecule, will there be a conformer which is sufficiently similar with a morphine molecule? So I will create a similarity library of all of relevant conformers. So to do that, I go to geometry and set torsions. You see there are they are pre-selected the three torsion angles. So this is will give me a list of a few dozen conformers, but not hundreds or thousands if it even gets bigger. So that's why I picked this one, or the tutorial works with this example. So then I go to setup calculations, and here go to similarity library, and maximum conformers examine 5,000, all fine. Do a submit, and my cephalene conformers will now generate the library, and this should be running and hopefully finish in finite time. So monitor. It's on 13 already, so it checks, which one, whether they are relevant or not. Previous 21, 26, and there we go, completed. So now we have, if I go here to the display dialog and look at properties, it found 27 relevant conformers for this molecule, and which are now in a library, and I need to close this library, save changes to it. Then we'll go back to my morphine molecule, and I'll actually do a similarity analysis of this molecule with the conformers in the similarity library. So I need to define what do I want to be similar? So I have to set similarity standards. So these are actually already predefined here in this model. So I have the choice either of structure, 9 atoms here like this, or chemical function descriptors, which would be here, the electron, here an aromatic ring, here the nitrogen, electron withdrawing, electron donating groups. So I will go here with the structure motif. So I will try to align basically the 9, 7, 8, 9, 10. The 11 atoms that you see here with a purple halo around them, we'll try to align it with this library, with the conformer library of cephalene, where there are 29 different conformers. So I go to setup calculations. That's the last option here, and we started with energy equivalent. Now here we have similarity analysis, and I have to. I will add the library, which I had previously done, but so I add it here again. And I'll leave all the other stuff intact and do a submit. And now this is very quick. It just compares this molecule with 29 conformers. So using geometric measures. So I go to display similarities, and now here there's first nothing because the minimum score was 0.9. If I lower the minimum score, what did I do wrong? So for the morphine. Oh, I did not switch here to structure. So structure and submit. Let's try again. And should finish in a matter of seconds. And I go to display similarities. And now if I do a reasonable cutoff for the point, so here there's a score here. I could choose the score if I made it. So the highest score was 0.9 for these. So I can make this big. But they're all these are all 0.9. 0.9, where 0.9 matches off. So superimposed here my morphine molecule and one of the conformers of cephalene. So now you can play the same game if one of these two, or if there's not a morphine molecule, but if there's a pharmacophore there. So I can define pharmacophores, and compare the pharmacophore with a library of conformers. Or I can even compare, I can create my own library of compounds. They don't have to be conformers. They can be, I can create a library of, my custom library of molecules and throw that into the, let's go, if I go here to set up, calculations. Here I was here in similarity. Here, add library. I could add here, add library. I could add here whatever I want. So these can be conformers. These can be a list of, stuff that I've, different isomers that I made or whatever. So, and then the game will be the same. It will try to do a match. So in general, you get QSAR related properties like some here. Areas, volumes, polar surface areas, accessible area, polarizability, and so on, log P. This can all be calculated also using polar surface area, for example, which is just based on a CPK model. It gets much better, if you actually work with a quantum mechanical model where you have electron density. You can calculate this, using the electron density rather than cartoon-like CPK spheres, and so on. Okay, so I've now already 10 minutes past when I wanted to finish. I will go back to the slides and wrap it up and take more questions. So this was here the functionality of the program for QSAR-related work, and one slide here quickly on education. So the program that you saw in action is called Spartan 20 currently. So which is a hardcore research program used all over the world, 3 platforms: Windows, Macintosh, Linux. There is a Spartan student version, which is significantly less expensive in all for education use. It is capped at for DFT calculations, for example, at 30 atoms, including hydrogens, 30 atoms. So this is not enough for research purposes. So it's like and for semi-empirical, it's capped at 75 atoms. So there are limitations. It's not it's a subset with, with restrictions of Spartan, but it's inexpensive for student use. Windows, Macintosh. We have another program for which is Odyssey, which is overlaps with Spartan, which goes in a different direction. I don't have time to talk about it. And this was almost my last slide. So this is really the last one. The brochure was already an attachment that Yatinder Yadav had, of the email that Yatinder Yadav had sent out. We'll be happy, to provide you with trial licenses and answer any questions. And I'll for that now for answering more questions, I will.
Thank you, Dr. Jargan, for the nice presentations. So now we will move to the question panel, which is remaining.
Yes.
So we have answered a few of the questions. Now, one question: How to do modeling for organic molecules? Already we have shown something. How to do modeling for organic molecules?
I don't know how to answer this question. I mean, I've been using organic examples throughout.
Yes, so. That's why I tell you, it is already answered.
Maybe actually what the question was more about organometallics. So because this is sort of always, sounds to be a little more complex. That I can say is that the DFT has advanced to handle the entire periodic table these days. So this is now all doable. So it's organometallics are just as much of a possible topic as organics, even though it's intrinsically. I mean, organometallic chemistry is more complicated. So,
Dr. Benzi, please.
Very good afternoon, sir.
Mm-hmm. Good afternoon.
Sir, I have a question that how can we correlate the theoretical spectral data with experimental data?
You can try out. I mean, if your trial license, try a few, not too exotic molecules and try the test. If you're online, it would retrieve the experimental spectrum from the Cologne database, for sort of middle of the road stuff, and you'll form your own opinion. It's like some, they will look different, but I can tell you, I mean, this is not sort of now, Warren Harriot's basically has spent the last few years of his life on this, of some, to refine this. It has the quality of the calculated spectrum has advanced to the point that we can now say this is a wrong assignment, of the experimental spectrum. Because if there are big gaps, so then it's either because the theory is bad, which is no longer the case, or this is the molecule that we did the calculation for is actually not the molecule that they thought they had seen in the experiment. And I could see there's a paper in Journal of Natural Products. I think almost 10% of they looked at 1,000 molecules. 10% were misassigned. So it's like it's hard. I mean, it's not. I mean, for natural products, an amount of natural products is not a. I mean, I'm very impressed by that. So.
Okay, sir. Okay.
Thank you,
Thank you
Dr.
very much,
Jagan.
sir. Thank you.
Thank you, Dr. Bindi. Our software is really thrown to give for your answers that you can compare the experimental versus the predicted. And in
Okay,
future,
sir.
we are planning one dedicated webinar for NMR only.
Mhm.
Okay, sir.
So
Okay.
we will invite you there. And
Okay, sir.
thank you.
Thank you.
One more question from Dr. Nirja Sinha. Can you please show the wave number of saddle point in IR spectra?
Yeah, sure. I mean, it's I mean, I can. It's the questions of units that you'll. I mean, you choose the units that you want to present it in. I mean, the default is wave numbers. So, or accuracy, or what is the question? Whether you can show it in wave numbers or how accurate
I,
is.
I just repeat the question. Can you please show the wave number of saddle point in IR spectra? Please elaborate.
The wave number of, yeah, I mean, I think I closed down I did not even save it,
I believe we can come down to this question in last if something needs to done for that.
yeah, it's like
Yeah.
so I had the I mean, okay, let's do something
You can run something. In the meantime, we can take other questions.
Okay.
Yeah. There is a question from Sangeeta Agarwal. How to get modeling for inorganic complexes? Okay, we have done some. We have not done. Yeah, the organic.
Yeah, there's some. I mean, inorganic. So if I want to do here, I don't know, some here if I tetracarbonyl or something like that. So
Yes.
there are tools available for all this. You know, some here. And if I want to put here and maybe an ethylene on there, and so.
As we did for the organic stuffs, we have a very nice toolkit for inorganic stuffs. You can draw lots of inorganic material and do your calculations. You can try with the trial license. We can extend you after this webinar.
Yes.
One more question is from Aditi Gangopadhyay. How Spartan for parameterizations of small molecules ligand for molecular dynamic simulations? Okay, sorry, we don't do dynamic simulations in.
Yeah, so we don't do, Spartan won't do dynamic simulations, and if you want to extract parameters from, so that's, you could, this is, you get energy points, for different distances, for different geometries, and now you will have to fit that, but you're a little bit there on your own, to use your own imagination. It's this, we don't have a canned way, a formula which will spit out new parameters for classical potential functions. That is not wired in. So get high quality relevant data, using DFT, with a good functional, significantly large basis set, high quality data for relevant geometries. That, of course, is right down its alley. So I mean, that's and with Spartan you will get more data, in a finite amount of time than with any other program, because you can do more calculations. So because it's simply all easier to set up. So, but then the final step to translate that to coefficients in some formula is still left with you. So I don't have tools for that.
One more repeated question. I believe we have answered that. Can we show comparison of experimental and calculated IR spectra?
Same question. Yes, the same. I mean, okay. I'll if you bear with me, so I'll do something, ethyl methyl ketone or something like that. So I will do, if I go to EDF2 from the Spartan database, replace. So for the EDF2 functional, which we no longer really promote, but the Spartan database always contains also the IR spectrum. So I simply go to the spectrum icon, and here calculated IR.
You're sharing? You're sharing the screen? Nothing
Uh,
shared.
yes. Sorry. Uh, yeah. Okay. The last there was okay. Something always has to go wrong. So the last 3 minutes, I was showing you I built an organometallic complex, and you didn't even see it. So sorry. I'll share. Yes. So I should not have gone back to the camera view for taking the questions. Yeah. So. No, yeah. So I just built ethyl methyl ketone. No, you're back in business, right? Yatindra?
Yeah. If you can see the
Yeah.
screen.
Okay. So here's the calculated spectrum, and I simply go. You can superimpose for ethyl methyl ketone is probably in the NIST database, experimental. So you see here this is I mean this is pretty good. So I mean this if you see here the and this was actually not the best density functional that you can do now. So but that is the you see here the frequencies on the right. I mean there was the previous question where for a saddle point, if you do this for something with a saddle point, a model with a saddle point in it, so then you would have one imaginary frequency. If you have multiple saddle points for multiple directions, multiple imaginary frequencies, that's what you want, if you want to identify transition states. Another word on that. And the previous model here I had shown while you was just hearing me and seeing the camera view. So I had gone here to the inorganic panel, whereas I mean here I'll build another one, so chromosine or something like that. So if I do periodic table, chromium, and here ligands, and put here benzene. I mean that's the simple example. So, but you see here the organometallic chemistry. We have the whole, as Yatindra had said, we have a whole set of tools to deal with this just as easily as with any conventional organic molecule: oxygen, nitrogen, hydrogen, carbon, sulfur, phosphorus. So no, you're not limited to that. You have the entire periodic table is easily available. So here's you can see here for the 631G basis set now is available for if you use DFT with one of the functionals that I mentioned. So you can do the entire periodic table excluding polonium, acetine, radon, francium, radon, actinium, and then here the transuranium elements. But all the lanthanides are available now. There are basis sets for these things. They are so it's the entire periodic table has opened up. And now with DFT, these things are on modern laptops will actually finish in finite amount of time. 10 years ago, it was still, semi-empirical PM3, where you were limited to these elements that you see highlighted here, or AM1, even fewer. But we can do better now. I mean, this is all a little bit. Semi-empirical is good to get a good guess, and but you don't need to stop there. So with DFT or Hartree-Fock, you can 321G. Here even 6311G star, which is a big basis set. Entire periodic table is available, including astatine. Who on earth is interested in astatine? So I guess some people are. So other questions?
Excuse me, sir. Excuse
Okay, Dr. Jagan.
Yes, sir.
One.
Thank you, sir,
Yes,
for your
ma'am.
nice
Yes, ma'am.
presentation. And I would
Yes,
like to know about the studies about the nanomaterials and the biological applications of any type of molecules, from small to bigger one.
Yeah. So let's start with biological molecules. You can easily, you can retrieve from the PDB database. It's like do no. Okay, minimize my ring central. So I go to Access PDB online. I think if I do it. Oops. So here I just retrieved, on the internet, because I'm on the internet, a structure from PDB. So there are typically, as in PDB, there are no hydrogens in it, but I can add. Actually, there's a tool to add the hydrogens. The program will add hydrogens to it. Display properties, molecule. I have to find now actually where that option was. Anyway, so you can display these things, but you won't do quantum chemistry on something that big. Okay, it's just not realistic. So, and you won't do conformational searching on something that big. What you can do. You can do you get to visualization. You can look at some basic QSAR properties, area, volume, polar surface area, ovality, things like that can be, once I have hydrogens there, you could calculate that. But you cannot do, the advanced molecular modeling calculations. So this was one of my first slides, 500, molecular weight 500 is really the limit for doing the real, hardcore modeling stuff. Docking also would not within the domain of the program. So polypeptides and polynucleotides, so up to 500, up to molecular weight 500. This is just a rule of thumb, of course. I can easily build, so can handle. So here I built here is the polypeptide builder. There it is. So that's here, reasonable. That is still, I can still do quantum chemistry on this. So this is not going to kill me, even though it will run for 30 minutes or something like that. So that is still within the, so this is about as far as you can go, with conformational sampling and all this stuff. So tube model, I can do, I can hear the build, minimize. So now use classical mechanics to minimize this. Can show the hydrogen bonds in the model here and so on. So they are the peptide, polypeptide, and polynucleotide dimension of biochemistry is perfectly accessible, and visualization of large stuff is no problem either. But so that's so nanochemistry, more like sort of materials chemistry. It's a similar story. If you very often people are actually interested in solid state structures, so they want, they work with unit cells, a certain space group and so on, and you do solid state calculations using plane waves as the basis set. So this is not the domain of physics, and this is sort of it's orthogonal to quantum chemistry using Gaussian basis functions. If you can formulate your materials question in terms of a cluster of, maybe 50 or 100 atoms that, they're sort of, like a super molecule, then you're in business. So, but you cannot do, and then the problem is, you cannot just do brute force sodium chloride or something like that without without having a unit cell, which is periodically replicated, because you get killed by surface effects. So Spartan will not do periodic boundary conditions. So physics programs will do that, like VASP or something like that, but Spartan won't.
Thank you, Dr. Jagan. So
Okay.
just come to the next question. Is it possible to study structure pruning QSR studies?
Mhm.
Is it
Ye-
possible to study structure pruning QSR studies?
Structure tuning, yeah, that's sort of, I mean, that means looking for comparing lots of molecules, look at how some properties, some, I don't know, polar area or partition coefficient or whatever, how it varies, by looking at lots of structures. That is sort of a natural for Spartan because we are so much, set up for handling lists, immediately. So lots of other software it's much more tedious because you can set up your one molecule, and then you do the next molecule and stuff. So some Spartan has always this global check mark. So you set the global check mark and it will do all of them at once. You still should be a little bit, run a little test so that if you run 100 molecules, try with one first, make sure that the one doesn't take 2 hours because then 100 will take 200 hours. So, little common sense is required, but the infrastructure is there to really to look at lists of molecules, at entire, it's sort of like combinatorial computational chemistry, you could call it. Okay, the program is really set up for that. A little bit of a learning curve, so you have to read the manual a little bit. It's not, you won't start with lists, as the very first time you open the program. You have to work a little bit your way up to that.
Thank you, Dr. Jagan. Dr. Anupama, what is the cost of the software? Okay, we will get back to Dr. Anupama and discuss on that. Now, the question is from Dr. Riaz Chelani. Can we have the potential energy diagram of transition states for every steps of reaction, and can we overlap them all?
Yes, it's like I didn't show the plotting facility at all. It's like some if I if I have I have a spreadsheet which has for potential energies, as you go along the reaction coordinates. These are just all similar steps along the reaction coordinate, and these energies are in a spreadsheet, and then I can simply go to the plot facility, and I will put on the x-axis, I declare what my axes are. I don't have an example now ready to use, which will show me, variation of potential energy as as I go over the transition state or whatever. For whatever list of, there's a comprehensive plotting facility with straight built into the program. You don't need to go to Excel or anything like that. It's all that is all there. So.
Thank you, Dr. Jagan. There is one question from Dr. Faji. How to make overlay diagram using Spartan? Overlay diagram using Spartan.
All layer diagram. It doesn't ring a bell. What's in? I don't know if it's the language or.
I'm also not very clear. We will come back to Dr. Faji and we will get a brief query from you and then reply back to you.
Okay.
Dr. Faji, you are there?
Actually, my question is how I will overlay our diagram if the result coming from XRD, single crystal XRD, and calculated diagrams. So I want to overlap both diagram. So how it is possible with the Spartan?
It's one of them came from another program, or both come from Spartan. Both diagrams.
No, one structure from the single crystal XRD machine.
Okay, and so this would be okay. What does this machine spit out? The spectra, or what does it spit out?
Crystal data.
Not molecules from the CIFs, crystal informations file from the XRD.
Okay.
And we have the molecules from the CIF.
Okay.
And other molecules from the Spartan. So
the program reads a ton of different formats
It reads CIF file. We can read CIF file.
Yes, it will. Oh, okay. The CIF file. Yes, it will. It reads CIF files. No problems. It does not, though. It sort of ignores, the crystallography aspect of it. So I don't. I want to. It does read the CIF file, but it's to be frank, it's not a terribly useful functionality because you are not, it doesn't translate it now into, like Mercury from Cambridge into a crystal structure. You just get, isolated atom positions, which is sort of a dead end from the point of view of using it in Spartan. So yes, it will read CIF files, but actually this is not something that you'll find. I'm always. I had the long slide of all the things which Spartan won't do. I want to be clear about what it won't be useful for. So it's not. It will read CIF files. It will read all kinds of other. I pulled up here I'm still sharing, right? So all kinds of other formats that the program writes and will also read.
Dr. Faji, our software can open the CIF file, but it is not dedicated for the crystal data.
Yeah. So
Okay.
So if you're really into crystal structures, and if you can take your crystal problem and translate it into a cluster problem, then we are in business. If what you really want is a crystal structure, I would encourage you to look for other software. So that's I think you'll be frustrated with Spartan.
The reason for asking, nowadays most of the paper I have seen, they are producing the overlay diagram with the single crystal X-ray machine and with the software like the Gaussian, and they are putting the overlay diagram.
Okay.
So
I don't know what Gaussian supports in that area.
Sir, I believe Gaussian also don't support this crystal data. This is not a program designed for crystal data. What I believe so, but I'm not very sure. If he has experience on that, he can be.
Yeah, if Gaussian supports it, then use Gaussian. I have no problems with Gaussian.
Okay.
Gaussian has its uses,
but,
no doubt
but
about it.
I'm doubt on Gaussian also. Gaussian is not written for this crystal data studies. Anyhow, the next question is from Robina. In some molecules, we get alpha and beta homolumo energy values. What are the reason behind that?
That's simply for if you have radicals. So you will get, if you have, if it's an open shell system, it's not a closed shell system. You get under a Hartree Fock, you get separate energy levels for upspin and low spin. Because it's no longer a closed shell. So it won't happen for boring closed shell molecules. It will happen for radicals.
One question from Neeraj Sinha. Can we calculate the band gap homolumo levels of metal oxides or semiconductors, or Spartan is limited to organic chemistry only?
No, it will calculate homolumo gaps straightforward for molecules or clusters of molecules. It won't do it for a crystalline structure that's periodically replicated. If you are happy with doing it for a cluster, let's say of 100 atoms, and you saturate the valences at the surface with hydrogens, let's say, in order to so you don't have open valences, then you will get for quantum dots or something like that, no problem. It will not do periodically replicated unit cells. So the band gapes, the classical band structure calculations, what the physicists do. It won't. It will calculate a homolumo gap for a molecule or a bunch of molecules that are close to each other.
One more question from Dr. Pradeep Pilani. Is it possible to check the model protein with Ramachandran plot or such sort of tool available in Spartan detection of active sites. You want to say something on that, Dr. Jagan?
Detection of active sites in proteins or something, or
Yeah, in protein only. I believe.
yeah, you can. I mean, the visualization is there, and you can actually extract the ligands from there. Actually, go to there's a tutorial on that in the one of the tutorials deals with extracting a ligand from a PDB structure, and and then analyzing that and finding drugs that will fit there, and that would also fit in the active site and so on. So there are you have there are aspects in this area that can be investigated with Spartan. It's not geared from the very beginning, dealing, with this sort of then leads to docking. I mean, there are lots of good docking programs. They are designed from the ground up, to deal with these large, large structures.
For docking and all, we have a different program. If you're interested, we can discuss with you separately.
Yeah. So.
Yeah. One more question from Dr. Ajia from Kuala Lumpur, Malaysia. Can we have an external participation like applied magnetic field, external electric field in the system? How about varying the temperature of the system?
External fields, no, not to my knowledge. There may be, no, it's not doable in any straightforward way. If it's doable, it's very arcane. No, it's not something not supported. Actually, it's a good item I should add to the slide, with what it can't do. So yes.
One last question from Dr. Anupama. Can we study DNA dash protein binding studies of organic compound and metal complexes?
Yes, I mean if it's DNA binding with polynucleotides, so with models which are not huge, and you can do with fancy DFT methods, and it's perfect to study that. It's just you won't. The system, I mean, it always goes back to, if you will, visualization, there are no limits. It can be huge. But if you want to do real calculations, meaning either quantum chemistry or conformational searching, it has to, hundreds of atoms will be fine. But once you get into the thousands, sort of you are out of luck. It's just you need a supercomputer. So.
One more question from Dr. Ria Salani. How can we differentiate between Hartree-Fock and DFT by using on any systems, or simply DFT is better than Hartree-Fock?
DFT has, I mean, if you look at has basically, Hartree-Fock is cheaper for structure, just for geometry, for bond lengths and bond angles. Actually, Hartree-Fock is, there's a lot of documentation of that from in the manual. And also a book that Professor Harry wrote, which you can obtain from Wave Function on quantum chemical methods. For simple bond length and bond angles, Hartree-Fock 631G is amazingly good. So DFT is almost as an overkill. Once you get though to energies, to transition states, you move away from ground state structure of closed shell systems. So now DFT kicks in big time, and it's now B3 LEP is still by far the most widely used. It's still used everywhere, and because laptops have gotten and desktops have gotten fast enough, you can afford to do that. What used to take weeks now can be done in minutes or hours at worst. So DFT has taken over big time. Also, semi-empirical has faded in relevance. Semi-empirical is still actually used also in all protocols as an intermediate stage. You start with molecular mechanics, classical, then you do semi-empirical to get a trial wave function, and then you start with the real with the real techniques. So
Thank you, Dr. Jargan, for the nice presentations. I believe there is no more questions in channel
Okay.
box. And it's midnight from you. It is 1:40 a.m.
Yeah, yes, it's 1:40 p.m. Yes, yes.
Yeah.
So,
So, any of the participants, if they want to convey vote of thanks to Dr. Jargan, they want to, anyone, if you want to unmute yourself, we are happy. Any one
Yeah.
of you.
Yeah, I'm amazed that I still see 48 participants. So yeah, almost everyone is still around. I'm very impressed by that, by your interest, and I'm honored to
Any one of the participants want to say anything to Dr. Jargan apart from our question hours? You want to say his feedback regarding our today's presentation?
they're all muted. So
You have to unmute yourself, Dr. Nirja Sinha. Yes, ma'am.
Thank you so much, Dr. Jogan, for this wonderful presentation. And yeah, so today, like, I could relate to most of the things, and I think I'm looking forward to use this software for my research purpose. Thank you so much for the wonderful
yeah,
presentation.
all right.
Thank you. Dr. Sangeeta.
Yes,
What is it?
thank you.
Yes, ma'am.
Thank you, sir, for such a nice presentation, and looking forward I am for using this software.
Yeah.
Thank you very much.
Thank you,
Thank
ma'am.
you.
Thank you, ma'am. Thank you, all of you. And we won't take more time of Dr. Jargan. Already we
All
have
right.
taken his sleep hours. My colleague Manoranjan is here. You want to say something, sir?
Nothing. I just want to thank everybody for taking time out to attend this presentation, and especially Dr. Jargan, who's it was supposed to be 1.5 hours, but now it has gone to more than 2 hours. So thank you, Dr. Jagan, for your time and your energy and your effort.
All right.
Thank us out.
I can
Thank
see
you.
Dr. Sisa is writing that no audio, sir. If you face the audio issues, no problem. We are going to share the recording with you. You can have get the idea what we have done today.
All right. Okay, I
Yeah.
will stop the recording.